All right, so now what we're going to do is to introduce what is called the Newton form of the interpolating polynomial. Okay, and so this is in contrast to the Lagrange form of the interpolating polynomial, which we first derived. So let me briefly recall for that to you. So recall that sort of the Lagrange form of the interpolating polynomial right is Pn of x is equal to the sum from j equals 0 to n of L and j of x, f at xj, where L and j is the Lagrange polynomial. So it's the product from I equals 0 to n for I not equal to j of x minus xi divided by xj minus xi. Okay, so the point is that this form of the interpolating polynomial is very inefficient to evaluate in terms of the number of floating point operations. So inefficient to evaluate in terms of number of iterations, number of floating point operations. Okay, so so when we first talk about polynomials as one of the possible things you could do interpolation with, one of the things I mentioned was that there's a very efficient way of evaluating a polynomial using what is called Horner's method. Okay, and so we're going to introduce a different form of the interpolating polynomial which lends itself to evaluation using Horner's method. So let me give you the definition of this Newton form. Okay, so the Newton form of the interpolating polynomial it looks like the following. I'm going to look for a Pn of x which is a0 plus a1 x minus x0 plus a2 x minus x0 x minus x1 all the way up to an x minus x0 x minus xn minus 1. Okay, so this is a0 plus the sum from k equals 0 to n of ak, the product from I equals 0 to k minus 1 of x minus xi. Right, I mean, in principle, you could sort of include this a0 term as well, as long as you understand that when there are no terms at all, the product corresponds, just gives you 1. Okay, so I can write this as the sum from, sorry, I had k equals 1 here. So I could sum from k equals 0 to n of ak, this product, as long as you know that the product from I equals 0 to minus 1 of x minus xi is just 1. Okay. All right. So yeah. Anyhow. Okay. So this is what is called the Newton form of the interpolating polynomial, and the reason why that is helpful is because it naturally lends itself to a Horner-like factorization. So let me sort of just show you what I mean by that. Right? So I can write Pn of x as a0 plus x minus x0, a1 plus x minus x1 multiplied into a2 plus x minus x2, and so on. Right? So, so that leads to this type of Horner type algorithm. So let me sort of write down the algorithm, and then the next thing which we'll do is to talk about, well, once you have the algorithm for evaluating, it's like a polynomial Newton form, we'll have to figure out, well, how do you compute the coefficients, it's like which allow it to be an interpolating polynomial. Okay, so the algorithm is as follows. Okay, so this is Horner's method for evaluating sort of the Newton form of an interpolating polynomial. At x equals to x bar. Okay, so the input is a0, a1 all the way up to an, which are the coefficients in the expansion. I need to know what x0, x1 up to xn minus 1 is, and I need to know what x bar is. And then the output is just pn at x bar, which I call p. All right, so I let p equals to an, and then for I equals 0 to n minus 1, I actually really want to sort of go from j equals to n minus 1 to 0. Okay, so in MATLAB you can actually set up, it's like the for loops, it's like with a negative increment, right? So it sort of goes down instead of up. But anyway, so I'm just doing this here, but in MATLAB you could just have j go from n minus 1 to 0 instead. So p is equal to p times x bar minus xj plus aj and n. So that's really just the only thing Horner's method is doing. So let me just sort of make a small remark as to what's going on. Right, so first pass p is equal to an. Next pass p is equal to an times x bar minus xn minus 1 plus an minus 1. Then p equals to an x bar minus xn minus 1 x bar minus xn minus 2. I'm going to put 2 and 1 here, plus an minus 1 x bar minus xn minus 2 plus an minus 2. All right, and you can imagine every time you pass through it, it's like it multiplies it by one of the factors, and then it adds a sort of a lower coefficient to it, and then eventually you get this expression here. Okay, so anyway, so that's this Newton form of the interpolating polynomial. If you can find an interpolating polynomial of this form, you can use a modification of Horner's method to very, very efficiently evaluate it, much more efficiently than trying to evaluate the Lagrange form of the interpolating polynomial. So the next thing we're going to do is to talk about how do you actually figure out what these coefficients have to be in order to have it be an interpolating polynomial. Okay, so let me stop here for now.